Hello and good afternoon, friends. Welcome to CEC-UGC live lecture. Dear friends, in this very session today, we are going to discuss about compiler design. What are compiler design? What this concept is. For this, we have with us in our studios Mr. Sarfaraz Masood. He is Assistant Professor in Department of Computer Engineering, Jamia Millia Islamia. So, I would like to welcome our guest, Mr. Sarfaraz Masood. Welcome to the EduSet lecture, sir.
Thank you,
I'm willing to know what basically compiler design is.
Absolutely. First of all, good afternoon to everyone listening to this channel. In this topic, we'll like to know more about compiler design as talked by Ms. Geetika. First of all, the first question that comes to us is what a compiler is. In simple terms, compiler is a system software that has a very basic and simple task of converting a program written in a high-level language to a corresponding program in a lower-level language. With this simplistic task of conversion of a program from high-level language to a lower-level language, this may look to be a simple task, but definitely involves a lot many complications and a lot more detailed design is involved in this process. So in this lecture, we would like to have more details about this very topic itself. Now, the first question that may come to mind, okay, fine, this is about conversion from high-level language to low-level language, but the point is, why do we actually need this conversion? Why can't we code everything in a lower-level language? Low-level language is good for the system itself because that's a language in which the system understands. That's a language normally in binary 0 or 1. But this is not the way we can code pretty easily for complex programs and complex processes that normally we have nowadays in our environment. So if, let's say, we want to design a bigger software or a bigger program actually using a machine level language or a lower level language, then a lot amount of coding would be required. So to get away from this complex task of coding drastically for using a lower level language, we choose to code using a high level language like C, C++, or Java, which provides us a lot many tools actually to code simply even for complex problems. By the help of these high-level languages, the process of writing a complex program gets easier. Then, if we have written a program in a high-level language, then this is not the way the system understands. So, to make the system understand, we need this tool actually. We need the system software called compiler. So, this is where it comes into picture. It makes our task easy. We have the program in high level. We need the program to be understandable by the system. So, we need the program in the lower level. So instead of talking everything in lower level, we write the program in high level language and then we give it to the compiler, which converts this high level language program to the corresponding lower level language program. So as simply said, let's just get ourselves into this topic more. Let's have some brief historical review about this topic. It's all about computing. It's all about making the system do the things for us. But initially, the things were not so good for early humans. Computation or doing some calculations were pretty stony things. But then in the 80s, the 1822 was a revolutionary time for the computers. Mr. Charles Babbage, as we all know, he gave the difference engine. It was in 1982. It was a complete mechanical machine, definitely a breakthrough. He's also considered to be the father of computers because of this great invention. But then the problem was how to program this machine. The answer was definitely by changing gears, by giving input through gears and those mechanical features. So if we need this machine to do some calculations for us, we need to switch gears, we need to give mechanical inputs, and that's the only way this machine is going to give answers. Then things changed quite dramatically in 1940s when we had the first computer actually that was called ENIAC. As you can see in this image, it's a whole lot big kind of a hall that has been occupied by this computer. It was quite big, but it was completely free from all those mechanical gears and switches. Now it was replaced by switches and those vacuum tubes. But again, still such a big thing, such a big problem it was. Again, the question was how to program it. If I want this system to do something for me, then how to do it? Again, I need to provide it input, and those inputs in this case was being provided by flicking those switches and giving those tubes some inputs. So it was an electrical way of giving input. But again, making this thing work was quite difficult. So if, let's say, I want this machine to perform some big program or solving some big problem using this machine, then a lot more difficult kind of a code would be given to it. Those codes will be definitely in the form of 0 and 1, and those will be provided using those flicking switches. So as it says, during 1940s, the code was normally hand generated at the binary level, that is the 0-1 level, and entered physically by switches. If we had to change the behavior of the system, or we had to change the program actually, then the system, the entire hardware had to be rewired. That was a big problem. So if from my hardware I want some other thing to be done, now it has to be rewired, the switches have to be replanned and everything. Then came the time of early 1950s, in which the initial attempts to the abstraction were made. Grace Mary Hopper is a very, very renowned name in the field of computers. She is the one who actually gave the first compiler known as A0, or the arithmetic language version 0. This was the compiler actually given for the UNIVAC system. This was a code written in assembly language form with simple English. So you can see that right from this 1940s to 1950s, the change was that instead of giving the inputs in the form of 0-1 commands, now we had something called the assembly language, which had commands in simple English statements. So you can see the difference, that giving inputs to the system in terms of 0-1 numbers, now we had the option of giving inputs in terms of English language statements. Definitely these are far more easy for us to understand and remember. So once we remember the commands, it's easy for us to even code them better. Then during the late 1950s, we had the Fortran coming up with its own compiler. This diagram actually tells us the kind of a brief overview about the various languages that have been there since 1950s till the date. Many recent one might not have been there, but it gives us a clear idea about from where we started and where are we right now. We started with the Fortran. At the same time, similar time, we had COBOL, ALGOL, and right now we are there in the age of Java, C++, and Ruby. Right from those initial languages till these complex modern day languages, the basic difference that has come up actually is the complexity or the ease that these languages they provide us with. They provide us with greater tools, better tools with which we can design programs in a better way. Complex programs, they look to be simply coded in these languages. If we think about coding these complex programs using the old days languages or the lower level languages, then those programs would look very difficult to even imagine. Going with the similar flow, in 1960s, ALGOL 60, the first language with a formal grammar specification was there. Actually, this was a time when language theory was better understood. It was the era in which this language theory it evolved and revolutionized the compiler designing process. As we can see, the first syntax-directed compiler was born in this time. Also, the Pascal had come into picture. The basic thing that we get to know from this era is that the primitive attempts at automating the compiler construction using elements from formal language theory were also made during this time. As we all know, the people from this field must be aware that the study of the formal language theory is very, very important and relevant if you want to understand compilerism. Modern day compilers are totally based upon formal language theory concepts, and that is also a case that if you want to go through this topic, you must have a good knowledge about formal language concepts and theory. So this was a time in 1960s when more of such theories and more of such concepts came into picture, which laid down in developing better compilers and modern day systems. 1970s, 80s, and 90s, they collaboratively lay down the foundations for the modern day computation. We have the C language actually coming up in 1972, which was distributed as a part of the Unix operating system. BASIC was also there in 1975. We also find compiler tools to be developed and used extensively. Actually, these are the tools which help us in developing those compilers. Also, during the late 90s, the success of PCs, they help in bringing the compilers and interpreters to everyone's desks and tables. So at the time when 1990s, when PCs were at a big boom, people started getting them from their offices to their homes. So nowadays we see that these PCs are now everywhere. So we cannot hide away from the fact that yes, compilers have also reached from offices to the homes. So directly or indirectly, we may wish or we may not, but we are using compilers and interpreters in our daily lives. So as it says, compiler today, they can be seen everywhere around. If you are programming in the strict sense, yes, definitely. As an application, we can think about it. We have languages actually now that sources compile into a document. We've got tools like MATLAB, in which we use a language to specify mathematical operations. We've got Verilog and VHDL, in which language is compiled to a circuit. So it's not like language is doing only the mathematical task. We are now doing documents, mathematical operations, and circuits. You name anything, it's there. So compilers have actually moved from big offices to the households. So now coming directly to compilers. As a discipline, it involves various core computer science and engineering areas, in which definitely programming language and algorithm is the foremost. One must have a good amount of knowledge as far as the programming languages and the corresponding algorithms are concerned. Next, very important, is theory of computation. That's another field of computer science and engineering in which you should be sound enough. So is software engineering. Compiler is a subject that definitely cannot be studied without the knowledge of computer architecture. Until unless we don't know the underlying architecture, it will be very difficult for the students to understand this topic. And so is the operating system, because the compiler has to interact constantly with the operating system to do various of its tasks. So all these, you can see, all these 5-6 topics are definitely necessary before moving on and understanding the compiler design topic. So the next line says compiler has a misleadingly simplistic intent. It looks pretty simple. You just have to convert the source program to the target program. At the same time, definitely if the program has any kind of problems, any kind of mistakes, then you need to issue error messages. But this may look pretty simple enough, but yes, this simple box that we can see in front of us is not as simple as we think in its design. Definitely the source program and the target program are highly varied. They're quite different in their nature. Quickly reviewing the various kind of compilers that we find, and there are various bases actually on which the compilers can be classified. We have classification based upon the construction. We have classification based upon the functionality. As far as the construction is concerned, we do have single pass compilers, multiple pass compilers, and load and go compilers. Single pass, as the name suggests, it's that you've got just one turn. In that one attempt, you scan the entire code, you try to find out all the errors, all the analysis, and in that very code, you try to generate the object or the target code. That is the only attempt you have. This itself is a difficult thing, because quite a lot of tasks and objectives are to be achieved while compilation is done. So attempting everything in one single pass is a daunting task. Multiple pass compilers are slightly more easy in their approach. You've got multiple attempts to go through over these source programs. In one attempt, you can do a certain task out of that. In the next attempt, you can fill up the gaps that were left in the previous attempt, and so on. So it's a varied architecture. You either go for a single pass or you can go for a multiple pass. Then we have something called the load and go. The load and go compilers are slightly different in nature. They do not tend to save the intermediate code in the system. They simply convert the source code into the object code, and then they directly execute that code from there. So no need of saving the object code into some file system. Then on the basis of functionality, we do have compilers of the type debugging compiler and optimizing compiler. Debugging compiler can be simply understood as the compiler which helps us in debugging process, whereas the optimizing compiler are the one which tends to optimize our code. This topic of optimization again may look pretty simple, that we're just trying to optimize, we're just trying to do it better. But again, it involves quite a lot of technicalities. The first question may come to mind, that why we need to optimize? The programmer is considered to be the supreme person. He must have given the best of the codes possible. Then why do we even think about the point of optimization? Because actually the task of this conversion of source code to target code is an algorithm-based thing. There's no human intervention in that. So this process may not be as smooth as we think. So while this conversion, we do feel that a lot of scope of improving the program that we have converted to are there. So we do not aim to optimize the source as it is. Rather, the converted code that we get, the object code that we get, we try to optimize that part. But we do perform optimizations at multiple levels. It's observed that we say that the optimization can be done at 3 levels, one at the programmer level, one at the intermediate level, and one at the target level. So even the programmer has the full authority to optimize in various ways. So although all these varied types utilize same basic concepts to accomplish the majority of these tasks. So they slightly vary in some portions of the design. Rather, majority of the part of the compiler design is almost similar. So we can see that it's a process of language translation, where we see that we have a source code being fed to the translator and a target code is generated, and this is actually with respect to the target machine. So we have to be very sensitive towards what kind of a target machine we have. So it's not just conversion, it's conversion with respect to a target machine. So to execute a source program written in a high level language, it is essential to translate it to a native code of the target machine. Just to go through quickly some basic terminologies, we have something called source code, which is actually a code being fed to the compiler. This is the one that has been written in most probably in a high level language. Then we have something called a target code, which is actually, as the name suggests, it's a target of the compiler. This is the converted code that we wish to achieve. We have the object code, which is actually also a part of the machine code or a part of the target, but once it gets along with the libraries, forms the final executable code. Whereas native code is a term that we use exactly for the machine. It's a code that is meant for the machine itself. As far as the terms compiler, assembler, and interpreter, we do it as like this. Assembler is, in simple terms to understand quickly, is also similar to the compiler behavior. The major striking difference that we see in an assembler is that the input to an assembler is an assembly language, and source, and that means the source to this system is an assembly language, and the target is normally a relocatable machine language. Whereas the interpreter has a slight difference in terms of the way it works. Interpreter can also be considered as a compiler, as the definition we have given previously. It translates and executes the source program, usually line by line. So it's normally understood that interpreter, they work line by line, they translate and execute the source program line by line. As it says in the next line, the target code is not stored. So there's no need to store the target code. You don't even have to convert the target code, convert to a target code in totality. You take one line, you convert it to, you translate it, and you execute it. So there's no need as such to store it. So that's why it's saying no need to store that code. However, compiler, as we have been talking till now, it translates and produces the target code that can be stored and reused many times. So we can see that there's a difference in objective as far as these three terms are concerned, very oftenly used in this field. As far as the design is concerned, we say that there are two fundamental components that we have given, or that we have proposed actually. We say this is an analysis synthesis model of compiler design. The first part is known as the analysis phase, and the second part is known as the synthesis phase. As the name suggests, the analysis part tends to analyze the source program, because that is what is being fed to it. So it's very much intuitive, as we do with our as we do in our daily lives. Let's say we read a text. So if we say that yes, we have understood that text, or we have now know what the text is trying to say, so definitely we have done these two things. We have analyzed the text while reading it. We have read it character by character, definitely, but the speed at which our mind is working is pretty good, so we don't get to really observe that thing. So we tend to read it character by character, then we form words, then we get together those words and try to see if the structure of those words is right, and then we try to extract meaning from those words. So the first of the major part that we do while reading is analysis. So it's saying that analysis is the task to decompose the source program into an intermediate form. So definitely we try to analyze the thing first of all, that what this thing is trying to say, is it right or not? We're trying to find errors from it. We're trying to extract information from it. And then once we have concluded that yes, analytically this is fine, is not getting any errors, we have extracted all the information required, then we actually synthesize this into the target program. So the next phase of the compiler, or the next portion of the compiler, is referred as to the synthesis phase, the target program generation from the intermediate representation. So as we just talked about it, analysis synthesis model, it breaks down the source program into pieces and creates an intermediate representation, while the synthesis part constructs the desired target program from the intermediate form. The operations implied by the source program are determined and recorded in a tree structure or similar structure. Normally we find a syntax tree or a parse tree over there. The node is an operation and children are operands. We may go through them later on more deeply. Okay, coming to this very well-known diagram of a language processing system. So in fact, compiler is a component of a language processing system. It's not a processing system in itself. We have actually a component called preprocessor that is actually fed with the source program. So source program is not directly given to the compiler, it's given to the preprocessor. So that is why you can see the word pre in it. it's doing before the big processing can start. It's doing something. So the source program is actually given to a component called preprocessor, which actually has a very important task of expanding those macros and hash defines. And once that expansion has been done in your source program, then what you get, as it says source program 2, then what you get is the actual source program on which your compiler works. So without those expansion of macros and hash defines, the task of compiler would not be right. So the source program given at its second level is actually the source program on which the compiler works. As we all have talked till now, that compiler has a task of generating a target language. Normally it is a target assembly program, which is then fed to a component called the assembler. And the assembler is a component that takes in the assembly language, and its task is to generate a relocatable machine language. This relocatable machine language is then given to a component called loader and linker, which has the connection to the various libraries and object files. Once you get these two things together, the relocatable machine code and the libraries, then finally what we get is the absolute machine code, which can be executed and run to get the answers from the program. So this whole lot of sequence of steps are to be followed if we wish to convert, if we wish to start conversion from our source program to the actual program that will run on a machine. And compiler is one component of a language processing system. So now we strictly talk about the various phases of a compiler. The first phase is known as the lexical analyzer phase, also known as the scanner. The next phase is the syntax analyzer phase, also referred as to a parser. Then we have the semantic analyzer phase, followed by the intermediate code generator phase, the optimizer phase, and the final target code generator phase. In all these phases, we also do have attachment with two more components. One is known as the symbol table, and the other one is called the error handler. As you can see in these names itself, the first three phases are carrying this word analyzer with them. That means they are a part of this analysis phase, and they have something to do with the analysis of the program. The first one does lexical analysis, the other one tries to understand the syntax, the next one tries to understand the meaning of the source program that you've given. So analysis is being done at the first three levels, and then you have the generators and optimizers in the next three levels. So this diagram tries to simplify the things that we have just studied. We get the source program, we give it the source program, if you all remember, at the level 2, which has passed through the preprocessor. So it's a preprocessed program given to the lexical analyzer, which analyzes the lexemes, or actually the word level analysis is done, which is then passed on to the syntax analyzer, semantic, the intermediate code generator, the code optimizer, and finally the target code generator, which generates a target program. As I said, that the symbol table manager is constantly in touch with all these phases, and so is the error handler. We say that at any of these levels, we can have a situation where when an error can occur actually. So this error should be handled properly and should be dealt with. The symbol table is actually kind of a database or a data structure that is an integral part of the compiler, without which actually this process of compiler design may not be, or the process of compilation may not be so possible. So it's actually whatever new information you get from the source program, you try to feed it to the symbol table. The symbol table keeps all those elements as a collection, and whenever required during the process of synthesis, those informations are then fetched. So you try to extract information from your source program, you feed them to the symbol table, and then wherever required during the process of synthesis, you extract those informations, you take back those information, you look up those information from the symbol table, and then you perform this task of conversion. So all these 6 phases, in one way or the other, are related to these two components, which are definitely required for the compilation process. So the first 3 phases, the analysis part, once again, we talk about it. It says the first phase is the linear or the lexical analysis phase. Just a simplistic view on it. It's a left-right scanning of the source program to identify tokens. Now we get introduced to a term known as a term called tokens. So first of all, this one thing is clear, that we are scanning the source code. That's why it's called the scanner. It's a left-right scanning, character by character scanning, definitely. And then we try to identify tokens. And it says token is actually a sequence of characters that we find in our source program that has a collective meaning to the system. So any sequence of character that carries a meaning to the system can be referred as to a token. That sequence of character may not be having a literal meaning to me directly, but if it's to the system, it's fine. For example, if we say in C int sum, that is SUM, then this sum is definitely, this SUM is definitely carrying a meaning to the system. It's an identifier. Similarly, I can have int XYZ. So XYZ may not be having directly a meaning to me, but as we can see in this program, that int XYZ is as an integer. So again, this sequence of characters is carrying a meaning to the system, so it will be called a token. So in short, we can say lexical analysis does the task of extraction of tokens from the source program. And definitely when these are being extracted, they have to be stored somewhere. So that is why we are saying we maintain symbol table. So whatever we extract from the source program, we start maintaining a symbol table and we start feeding them into it. Once this process of lexical analysis has started, it is followed by a process called hierarchical analysis. It's in short that the words that we have in the sentence, the group of tokens we have in a sentence, are they following the right order or not? Are they grammatically correct or not? As I gave the example of our own reading, we not only read the words, but we also try to go through the fact that are these words ordered in the right way as the language says. So the hierarchy of the tokens or the hierarchy of the words should also be checked. So the same way we do it, the system also has to do it before processing this component. So hierarchical analysis is the process of grouping tokens into meaningful collections, or actually we can say that it's a process of also checking whether the tokens that we've got in a sequence, are they right or not. If they are not correct, then you have to report the matter and handle this error properly. Finally, in this analysis section, we also have something called semantic analysis. Now, a sequence of tokens may be kept in the right order, but do they collectively mean right? The meaning part is also equally necessary and important. Just by checking the words, the spelling of the words, the order of the words is not the only task to be performed. We also need to check whether these tokens collectively mean something valid or true. So the task of checking to ensure the correctness of the components is done by semantic analysis. It's a very, very important task. This is the place where actually the meaning of the various components of my source program gets extracted and gets fed into the symbol table. Now we slightly go more deeper into each phase to understand them better. The first phase, as we said, is the lexical analysis phase, also known as the scanner or scanning task, linear analysis, or even in some ways it's also referred as to lex. It's not as complex as the syntax or the semantic analysis phase as far as its own task is concerned, its own work is concerned. It simply has to read the stream of characters in the source program from left to right. The moment it finds or identifies a token, it has to acknowledge that fact and keep it into a symbol table. Also, if the token has been identified, it has to be transferred to the parser for further processes. It also discards the white spaces, the tabs, the new line characters and comments in the source program. While writing a source program or while writing a code actually, we tend to give those white spaces, we tend to give those tabs for formatting, we also give comments for our own good. We tend to give new line characters for the proper hierarchical order of the program. These are all for the beautification part, these are all for the better understanding of the reading part. They have nothing to do with the semantics of the program. So these are not needed by the compiler whatsoever. These are not needed by the symbol table actually whatsoever. So they have to be discarded. All white spaces, all tabs, all new line characters have to be stretched out from my source program. And this very important task is done by my scanner. The scanner even takes care of the case sensitivity of the language. So if let's say my language is, let's say it's case insensitive, then in that case all the characters in my language they can be converted to a single uniform case sensitivity. Followed by another task that it breaks the source program into individual meaningful lexical units or lexemes collectively called tokens. So it reads the characters one by one. It tries to identify the lexemes in them, and the moment it finds a token, it raises an alarm, which are sequence of characters with a collective meaning in the grammar for a language. Tokens can be classified into the following types. We can find tokens in the form of identifiers, we can find tokens in the forms of keywords, numeric constants, string constants, and operators. So whatever various types of things we find in the system, in our source program, we try to name them. And any collective meaning, if they carry, then we call it a token. So token, as we said, can be identifier, keyword, and so on. What are non-tokens? So non-tokens, in short, are things that we don't want to take care of. So they can be comments, should be stripped out. They can be preprocessor directives and macros, blanks, tabs, and new lines. We're not bothered about them. They should be taken out of our source program, should not be carried forward to the other parts of the compiler, should be left here itself. So it's kind of a filter for our source program. And in fact, this is the only phase that has any kind of interaction with the source program. Once this phase is over, once the task of this phase is over, no more interaction with the source program will be there. So this is the only phase that has a direct contact with the source program. So all those filtering and those pruning tasks are to be done by that phase only. As an example, we can see that these are the various components that we find in our program. It can be an identifier sum, it can be an identifier result, area. We also have numbers in our programs, 20, 0, 34. We can have real numbers as well, 62.1, other examples. We can also have keywords like if, operators like assignment, equal to, plus, and so on. So all these things, all these characters, they mean something to the system. So simple definition, as we have been saying again and again, if they are carrying any meaning to the system, collectively together they can be called a token. So we just, for our own good, we have divided them into various types so that we can understand at various points at which kind of token we have received in our source program. So this slide just tries to represent the main objective of lexical analysis is to identify tokens which are the basic building blocks of the source program. So it's again, it's been said in a different way that the source program is built up of various tokens. So a number of tokens together, they form in a meaningful way your source program. We just taken a code snippet which says, let's say result is equal to init plus rate into 50. So all of these things are tokens. The result is an identifier, equal to is an assignment operator, init again an identifier, followed by a plus operator, followed by an identifier. So all these characters that we find here, either individually or collectively, they are tokens. And what is left out are again blanks and everything that we have discussed earlier. So as in the previous example, we're just trying to reformat that. What are the stream of tokens generated? The following is the stream. We have an identifier followed by an equal to operator, followed by an identifier, followed by a plus operator, identifier, multiply operator, the number, and a semicolon. So this is a sequence of tokens being generated once this process of lexical analysis happens. So you strip out all these valid tokens, you feed them into the symbol table, and also pass it on to the parser. So once your task of lexical analysis has started, the next important task comes into picture is syntax analysis. So what the sequence of characters that you have been reading in the earlier phase, if they are coming in the right order, if they are coming fine, this is to be checked actually. You've got a token followed by another token followed by another token. So are you getting the tokens in the right order? Now the first question that comes into picture is who decides the order? It's actually the grammar. The language for which this compiler is working is having definitely a grammar, and that grammar is deciding how the rules should be written in this language. So that is the checkpoint, that is the measuring gauge actually. If the tokens are coming in the right order as per the grammatical rules, everything is fine. If you find any discrepancy, you report that. Main task is to group tokens hierarchically into a grammatical phrase known as a parse tree. So if you're getting the things right, if you're getting the tokens right, you start forming an abstract representation known as the parse tree. So we also say that the parser takes the tokens and generates the parse tree if everything is fine. It determines the syntactic structure of the program and of all individual statements. Definitely it tries to detect errors in the statement which are violating the grammatical rules. For example, we again take that the code snippet, result is equal to init plus rate into 50. At the left hand side bottom, you can see over here we have given the grammar actually for writing that statement. So this statement must have come from that very from this grammar. So it says S derives ID equal to E, where an expression can be derived from E derives E plus E, or it can be E derive E star E, E derives ID or num. These are the various productions actually that we have. So this sentence that we're talking about has actually come up from this very grammar only. This can be verified, or this can be proven by the help of this tree. This is a parse tree actually. This is trying to show that this sentence that we have got is achieved actually from this very grammar. So the root node is actually the assignment statement, or in short the one we have taken as S. So it says that ID is equal to E expression and semicolon, the first half of the tree you can see the initial node, where ID is actually the result part from our source code snippet. The right child expression can be further expanded into expression plus expression. We have the rule in the grammar specified for that, where expression can be driven through ID. So all these nodes that you're getting in this tree are actually coming from this grammar only. So this grammar is deciding the tree, and actually the grammar is actually deciding the sentences also. So if you find any discrepancy, let's say the equal to sign is about to come in the beginning, or this is the first thing that you get in the beginning of a new sentence. So you find no rule whatsoever. The grammar is not giving any rule whatsoever which says that your sentence can begin with an equal to sign. It says your sentence can begin only with an identifier. That is again the reason why we do not have an expression on the left hand side, because we don't have any rule for that. So even syntactically we will be wrong. So this syntax is actually guiding us that this is the only way this sentence should be there. So we can check it, we can cross check it with the help of this grammar, that are we writing it or are we giving it in the right way or not. So this syntax tree is a proof of the fact that yes, this parse tree is actually a proof of the fact that yes, this sentence is definitely possible by this grammar, and is indirectly grammatically or syntactically or hierarchically correct. The syntactical or hierarchical structures of a program are usually expressed by the help of recursive rules. We all know that recursion has a very important is actually a very important property that plays a very important role in defining various languages. For example, why we say that things are recursive. For example, definition of an expression. You look at the previous slide, you can see the definition of an expression. E derives E plus E. That means the definition of E is dependent upon this E itself. It says any identifier can be an expression, fine, E derives ID. Any identifier can be a number, again fine, it's E derives num. And then I'm saying that if expression and expression are expressions, so are expression plus 1 and expression plus 2. So as we see in the previous slide, so look at the second production and the third production, E plus E and E star E. They again form an expression. So expressions are a part of an expression. So this is a recursive behavior. So we can see that this recursive behavior is being expressed very popularly by the various statements in our program. We find them pretty often actually. We find this recursive behavior pretty often in our programming languages. The lexical constructs, normally, if I talk about only the lexical constructs, they are not recursive in nature. That is why we do not need to define context-free grammars for them. We do not need a push-down automata for them. They can be simply identified with the help of regular grammars or finite automata. The task of identification of token can be done using a simple linear scanning. Hence they can be formalized only by regular grammars. Students from this background must be aware of these categories of grammars: the regular one, the context-free, the context-sensitive, and the unrestricted. So the lexical constructs are not recursive in nature. So if they are not recursive, there's no need for us to go for a complex solution and design a push-on automata for them. This task can be simply done by regular grammars, and hence we can simply design a finite automata for them and do the task of scanning. So scanners are normally implemented using those finite automata only. However, the syntactic constructs are often recursive. Therefore, they are formalized by the help of context-free grammars only. And to implement that, we need a push-down automata, a different class of or category of automata. Linear scan is not powerful enough to analyze such recursive expressions or statements. Then once this task is successfully done, we have the tree with us. This is followed by semantic analysis. Semantic analysis is actually trying the process of extraction of meaning. Syntax refers to the structure of the program, whereas semantic refers to the meaning of the program. So semantic analysis, we're trying to extract the meaning from it. What does a component in a program mean? If I say int a, then what are the various facets to this a? What does this a refer to? What do we mean by that? We've all understood by now, by programming so much, we have all understood that if I'm writing int a, then a is an integer. It's carrying a certain data type, actually that's of integer type. Its size will be of some fixed quantity, maybe 2 bytes, maybe 4 bytes. Its width will also be of some fixed notation. So all these things we immediately associate the moment we try to say that yes, semantic is there. So this definitely looks like something very intelligent being done, but yes, we write some rules by which we try to extract those meanings. Semantic analysis ensures that various components of a program fit together meaningfully. Even in an English sentence, if I say that everything is fine in a sentence as far as the words are concerned, but still they may not mean correctly everything may not feel correctly good at the same time. Let's say I say the sentence that she is a boy, a very simple sentence. Everything is fine, the pronoun is at the right position, the noun is at the right position, the helping verbs are there, but this sentence collectively doesn't mean right. So similarly, there may be many instances in our source program where things may be ordered correctly, but they do not mean correctly. I may try to assign an integer to, let's say, a function, or this may be correct, but we may try to assign, we may try to have two different data types on the equal to both sides. So this may not be right for us to do. So all these checking is to be done. Are we doing the types? Are we writing the types properly? Are we assigning the things properly? So the meanings part is definitely very important. A tedious task. An altogether different approach is applied while performing the semantic analysis, but it's definitely an important part of the compiler design. Maybe a part of the intermediate code generator. Type checking, which is again, as I was just talking about, is an important task that is performed in this segment, in this section, where we try to check the types of the expression, we try to check the types of the statements, and then we try to check the collective type of the entire program. Is everything fine in it? Are we doing any type mistakes or what? Let's say the if statement is supposed to have a boolean there. If, let's say, in our language, the if is supposed to have a boolean within the brackets. So are we giving the boolean there or not? Are we giving some float there, or are we giving some character? So the type of the data that is to be provided at a certain point, is it correct or not? It's the task of the semantic analyzer, not just type, but many other things to it. Attempts to identify more complex semantic errors are also there, and also the support of the process, and also the support to the process of code generation. All the information extracted by the semantic analyzer are fed to the symbol table. That's why we saw that connection between the symbol table and the semantic analyzer. And then these collected informations are then looked up actually into the table. They are needed because for the task of conversion from source, for the task of conversion, we may need those information definitely. So all those extracted informations kept in the symbol table will then be needed by the code generator. So that is why indirectly the semantic analyzer is also helping that process. Parse trees may also be augmented with some semantic actions to perform certain tasks. Let's say we need to add up this task of conversion of integer to real at a certain point. So such provisions are also there. Such actions can also be taken during the task of semantic analysis. To summarize well, we can say that to check if operands of an expression have the valid types, if we talk about type checking in semantic analysis, can even apply coercion. Coercion is implicit typecasting. If the language permits, for example, we say result is equal to init plus rate into 50. If the context is a float data, then the integer 50 will be converted or coerced to 50.0. That means if, let's say, at this point of time, we need this 50 to behave, let's say, as a float, then we can do it, although this may look like to be an integer. So such type conversions which are not there, but if we expect the machine to do, then yes, we can do it. We all know that in C, if we try to assign a character to an integer, then the ASCII of the character is given to the integer. So this initially looks like to be a type error. A character cannot be assigned to an integer data type, but a coercion is performed over there and type conversion happens. This is also because of the semantic analysis helping us in performing all those separate tasks. Also checks if variables have been declared before being used in the program. Very important. We may have started just writing the program. We all are taught that yes, we must remember to declare the variables. Declaration is a very important statement in the program, because this tells the compiler that what kind of variable is this one, the one we are talking about. So this task of checking whether the variables have been declared or not, are we directly using them in the program, have you forgotten to do that thing? So this can also be alarmed by the semantic analyzer if not found. So at this point of time, we would like to discuss something about the symbol table as well. As we have talked quite a lot, we say its creation happens during the lexical analysis phase, and it also gets in touch with the syntax analysis phase, is then filled up by the semantic analysis phase. So what actually symbol table is? We can understand it as a data structure that serves as a database for the compilation process. So why we are saying database? Because it will be storing those tokens that we have found at the various stages, and the related informations regarding those tokens that we have found during the compilation process. So all those things will be fetched up, will be fed up into these into the symbol table. Contains information of each identifier or a token defined in the program regarding its type and attribute entered by the scanner, and definitely the attributes that you extract are added later. Therefore, it is essential for a compiler to perform the important task of symbol table management. One has to be very clear as far as the management of symbol table is concerned. There are many problems that we may come across while maintaining this symbol table. We normally find that there's a property of scope of every variable. So we also need to assure that the scope of the operator is the scope of the variable is also valid enough. So we need to store it somehow. So all those cases have to also be dealt properly by the compiler. So symbol table management is an important task. So is the case with error handling. All these phases can issue errors. They can generate errors. We can come across errors in almost all the phases of the compiler. These errors must be detected and properly reported to the user. Once an error is detected, it must be dealt so that the compilation may proceed further. We would definitely not like to stop the compilation process the moment we find the first error. Imagine we are trying to analyze something, we come across an error and we stop the working. So that is something we really don't want. We want that maximum number of errors can be identified at a certain level in the compilation process. So as it says, further errors could be identified. A compiler which stops at the first detected error may not prove to be helpful. Syntax and semantic analysis phase typically handle most of the errors that we normally encounter in our daily life programming. Then comes an important phase that's called the intermediate code generation phase. Intermediate representation is actually a representation that has got many benefits to it. It's a representation that is not too far away from the source, but not even not even too far away from the target. That is why the name intermediate has been given to it. It's having the properties of the source as well as the properties of the target language. It's usually a program for an abstract machine. For example, assembly language. IR should be simple enough to be easily produced and also translated into target code. Now the big question may come up, when we know how to convert the source to target, then why are we adding up this extra step? So as we said, this process of conversion is a big leap. So instead of taking a direct leap, it's always better to have a shorter one. You convert it into an intermediate form. The advantage that we get is this intermediate form normally is machine independent. It is something that has nothing to do with the underlying architecture. So this will be your own representation. And the big advantage that we get over here is the optimization. We have not done any kind of optimization as yet. Once we convert this source code to an intermediate form, we've got a whole lot of opportunities to actually to get our code optimized. So optimization at a bigger level can be done in the intermediate representation. Machine code is actually difficult to optimize. So if, let's say, we have an example when we converted the source directly to the machine. So in that case, if we attempt to optimize that code, then those optimizations are pretty limited. We do have those optimizations. It's not that case that only the intermediate code can be optimized. We also have machine dependent code optimizations, but those are pretty limited. They have pretty limited effect. So they should be performed, but they do not give a global perspective. They do not give a global effect. So it's better to have intermediate representation and then try to optimize those intermediate code that we have generated. We'll definitely get a better answer or a better executable program. IR can be a 3-address code, normally a TAC or 3AC. Here instruction is allowed to have at most 3 operands and 1 operator along with an assignment operator. The example that we have been doing throughout this lecture, result is equal to init plus rate into 50. A short example can be shown over here. As we can see, the last operation of rate into 50 is done as one element. We have one 3-address code statement, temp1 is equal to id3 into 50, that is one line representing this operation. Then we have another statement of 3-address code saying id2, that is the second identifier, which is init plus temp1, the result that we have got in the previous statement. And then finally we have the last statement which says id1, which is actually result, identifier 1, the result is equal to temp2. So these 3 lines of 3-address code representation are actually representing the same code that you have. But this is much more a simpler representation, much more closer representation to the target. Conversion from here to the target is a simple process. However, the conversion directly would have been a difficult process. So a big leap is always a difficult task. This would definitely ease our things. But as we can see over here, the possibility of optimization has increased. The bigger the code we have, the more opportunities we do get for the sake of optimization. Immediately jumping to the optimization part, this phase of the compiler attempts to improve the code. Definitely the intermediate code that we have done, greater opportunities are available there. This is usually done for fast execution of the resultant code. However, the code may get shorter in length. That's an advantage for us. For example, the one that we've taken earlier, as we can see in this previous slide, we have this case, these three address code lines are now shortened to 2 3 address code lines, and they still mean the same. So this would not have been possible directly, because the process of conversion of source to intermediate is a typically algorithmic process where we cannot take such extra burdens at that very moment of time to optimize the code also. So we have a separate process for that. Once we have generated this 3 address code, we use this phase of code optimization. By the help of this, we try to reduce that code. So this code that we may have generated may not be the best one, but by going through this phase, we try to ensure that this is definitely better. Optimizations have definitely some few basic objectives. Definitely to improve the performance and the speed of the program, the one that executes. The code size, we also expect it to be reduced. So is the power consumption. Now is a green error actually. The lesser my code consumes power, the better it is. Fast compilation. We want the things to be more secure, and the debugging also to be easier. So with these advantages, mainly actually we need to cater the advantage of performance and size actually, and nowadays it's more about performance. As we can see, this is a code snippet written in any language. This looks like to be a C program or a Java program. In this we have a function followed by a loop within it. So just to highlight the issues that where the optimization may be possible, you can see that within this loop, this k plus 2 is being evaluated twice. There's no need to evaluate it twice. We can once we convert this to intermediate form, this re-evaluation of k plus 2 can be avoided. So are many other options that we do get. So such a big core has got a great amount of possibility of optimization once it is converted to a lower level or an intermediate representation actually. Just to name a few optimizations that we find in intermediate representations: common subexpression elimination, constant folding, dead code elimination. As the name suggests, if you have got any kind of dead code there which you think that will not, which you believe actually will not be executed during the runtime, it's better to avoid that. Loop invariant statements, some statements whose value actually is not going to change during the execution of the loop are better to be removed from the loop. So such statements should be removed from there. This process will be called loop invariant statement removal. Strength reduction, if possible, try to reduce those divides and multiplication operations by simpler and less complex operations that will help you in speeding up the things. Register allocation, I may not be able to talk about this deeply, but this is definitely a very important part which we may cover up in the upcoming lectures. Execution time of the program can be greatly reduced by performing these optimizations. Finally, we have the last of the phase of the compiler design, that's the code generation, having the main task to generate the target code, which can be actually relocatable code. That means you generated it on one machine and it can be taken to another machine and can be executed there also. Translates an intermediate instruction to a sequence of machine instructions. Optimal register allocation is definitely a challenge to be dealt with in this phase. How the registers that are there, registers are very limited in number, as we all know. So what kind of code should be generated that tries to have an optimal register allocation done? That is always a big challenge. So for the same example that we have been doing till now throughout the slide, this is the so-called the assembly for that. So we try to load this value into an identifier, from the identifier to register 1. We try to multiply that with 50. If you remember, it was the first operation to be done. Then we load the result into register R0. We apply R1 to R0 and so on. This can be understood simply in the later sections of the slide. So we can say that The compiler is also given a few more names. Its phases are given a few more names. We also say that compiler has a front end. It also has a back end. Normally, the first 3 phases of the compiler are referred as to the front end of the compiler, and the last 3 phases are normally referred as to the back end of the compiler. The analysis part is normally done in the front end, whereas the synthesis part is more done in the back end of the compiler. The compiler, as we discussed earlier, can have many passes. It can be a 1-pass compiler. It can be more than 1-pass compiler. But we do have to deal with some design issues if we're talking about a single-pass compiler where everything has to be done in one single pass. Need of multiple pass, we would like to emphasize on this issue also. There are many cases when all the answers cannot be given at one go. Some issues raised early in a program during compilation may remain unanswered until later, and when their answers are encountered. For example, if we try to refer to an identifier function defined later. So such answers cannot be given if we don't have an answer of a certain thing at a certain point. So it's better that we try to leave it there itself and try to fill up the gaps in the next pass when we try to rerun the thing. We also may not have enough memory to do everything in one single pass. That's again another reason why we normally go for multi-pass compilation. So we've discussed all these phases. Just to have a quick review about the compilation process. We started with this example of result is equal to init plus rate into 50. After the lexical analysis phase, we extract all these tokens, ID1, ID2, ID3 and the number. This is followed by a syntax analyzer which has generated this syntax tree for it, and it has also passed through the semantic analyzer which actually has done the annotation, which we cannot find it too deeply here. These phases are directly in touch with the symbol table, and as we can see, the symbol table has now got result, init and rate. These things have been assigned to it. So we do have the numbers. We also have the errors, if any generated. They are in touch with the error handler. Once this answer is achieved, we feed it to the intermediate code generator, which tries to give us the intermediate code. So we can see the intermediate code has been generated. Example over here has been taken of the 3-address code. Then we try to optimize this 3-address code, and we can see that this code has been shortened. The 4-line code is now converted to 2-line code. Definitely we expect it to be faster in nature as far as the execution is concerned, and it also occupies lesser space. And finally, we can see that this final target code generator has done its task and converted this 2 lines of intermediate code to a corresponding target code of a few number of lines. So this was the task to be accomplished, and compiler has all the technical advantages and the features to accomplish this daunting task of conversion of source program to a target program. For further study, you can consult these contents, Compiler Principle and Techniques and Tools. It's a very good book by Alfred Aho. Aho means SETI, normally we refer it to. Also another book by Engineering a Compiler by K.D. Hooper and Linda Toxin. Thank you.
Thank you so very much, sir, for delivering such a nice lecture, and I hope all the students from the computer engineering would be benefited from this very lecture. And with this note, we take your leave, and I would like to tell you that Mr. Sarfaraz Masood would be us tomorrow also, and we would be discussing a new topic.
Maybe on similar way. Yeah.
Exactly. Thank you, sir. Thank you so very much.
Thank you so much.